Hello and welcome to our today's live webinar with the topic Securing the Software that Runs the Internet of Things. This is a joint webinar from Vector and Semmle. I would like to introduce ourselves. Our guest speaker in today's live webinar is Kevin Backhouse. His role is a security research engineer at Semmle. The second speaker today is my colleague Ingo Nichols. He's Senior Field Application Engineer at Vector. And last not least, my name is Winfried Schröder. I am Business Development Manager at Vector and I will guide you through this webinar today. So, what's the plan for today's live webinar? I will first give you a brief overview about Vector. This will be followed by a short presentation from Ingo where he shows how VectorCast supports the development of secure software. And after that, Kevin will give us his presentation about the securing of software that runs the Internet of Things. And at the end of this webinar, we will answer all your questions. You can ask questions during the presentations by using the Q&A window. Here are some facts about Vector Informatik. Our main office is located in Stuttgart, Germany, and we have subsidiaries worldwide. Vector has around 2,000 employees in 24 locations in 12 countries and more than 7,500 customers worldwide. The Vector Group provides software testing solutions for all phases of testing, from low-level software testing to full system testing. Testing can be done natively on a PC or done on a target hardware at all levels. With the VectorCast product family, Vector is specialized in the testing of embedded C, C++, and Ada applications. VectorCast is designed for the development of safety-critical software in all industries where evidence for functional safety has to be provided. If we look at the V model, we find the VectorCast solutions at the bottom and on the right side in the rear of system and unit test. What you can also see here is that VectorCast can be integrated with many tools that you may have already in use. As you can see, VectorCast integrates with nearly all embedded compilers on the market. They are supported by 100%, and important to know is that you can test the source code exactly as it runs on your target system. We think it is always valuable to see where you are with the test process and think about where you want to be in the future. Different organizations are at different places across the spectrum. We are going to help you reducing the time it takes to test, increasing the frequency of testing, expanding the responsibility of developing quality software within your organization, increasing the amount of testing you have automated. VectorCast helps you to move all these bars to the right. Especially for the development of safe and secure embedded applications, it's probably good to know that the VectorCast product line is certified by TÜV for regulated industries. We provide also certification kits to prove the suitability as development tool and to show that the software is well tested. So that's it from my side. I like to hand over to Ingo and his VectorCast presentation now.
Yes, thank you very much. Yeah, hello everyone. Warm welcome from the beautiful city Kempen in Germany. My name is Inge Niklas. I am field application engineer at Vector. That means I'm responsible for doing technical support, so I'm a technical guy, and I'm responsible for VectorCast. And that's what I'd like to show to you today. I'd like to show VectorCast. What you should see on the screen is a little bit of code. We see on the top left side there are some C files. This is the Lua project, an open source project where we did a little copy from Git, and we did small little changes for the purpose of this webinar, but in general, it's the Lua interpreter that computes or interprets the Lua script language. What we did is we instrumented the source code to measure code coverage. And what you see on the screen on the right is we already have some code coverage on some lines in the code. We see green lines for lines that were executed. We see yellow lines for lines that are partly executed, and the color red shows us which lines were not executed yet. So this coverage, you may wonder where this coverage comes from. It comes from executing the code. So we executed the Lua interpreter, and we can do this, for example, using a command shell. We can call the instrumented version of the Lua executable together with a file, in this case all.lua, which has some Lua script. So this just executes the code. And the nice thing with Vectorcast is we can measure the coverage that we achieve on the Lua interpreter when this code is executed. It results in a file. There is one file called testins.dat, and this is where we store the code coverage that we achieved from executing this test. So we can even look at that file. It's an ASCII file. It can also be generated executing the code on an embedded device, so it does not necessarily have to be under Windows. It can be under Linux, and it can be on an embedded device on any RTOS. And this coverage information can be imported back into Vectorcast. We see this is the file, and now we can name the coverage according to the test case. In this case, it's the Lua script all.lua that we executed, and this is the additional coverage that we achieved from running this Lua script. Now, the nice thing with Vectorcast is we do not necessarily have to do this manually. When we close this view, then we see that in our Vectorcast manage, we have a Python script on that coverage environment. And the Python script is able to execute all test cases. The things that we did from the command shell can also be automated by Vectorcast. That means we can automatically execute the test cases, and we can automatically store the coverage into the cover project and name the coverage after the test case. So, for example, when we look at the interactive execution, then we get a list with all test cases. Where does this list come from? Well, as I might have mentioned, there is a Python script, and the Python script, we told the Python script to dynamically build the list of test cases from all files that we find in one directory, all Lua files that we find in one directory, and this automatically creates the list of test cases. Now, this test case list can, for example, be created by looking in a folder, looking which files we find. We can ask Google Test what kind of test cases do you have, and then run Google test cases. We can ask Canoe what test cases do you have, and then run Canoe test cases. So this Python script is adaptable. You can change it to run any kind of system tests that you'd like to run. Now the interactive execution, when we select one test case, for example, we can run this one test case and it will automatically execute the Lua interpreter with this Lua file and store the coverage into the cover project, or we can tell Vectorcast to automatically execute those test cases that were not executed before. So far for the cover tool. The cover tool not only allows you to execute test cases and measure coverage from system testing, we can also look at a dashboard. The dashboard has the information, the coverage information on the project. It shows us which files were covered and how well they were covered, and it also shows how big are the files and how complex are the files. We see this dashboard here and this a heat map in the middle of the screen, and the heat map is interactive, so we can it's hierarchical. We can click into this view and then look at coverage on different levels. For example, the coverage of one C file or the coverage of a subcomponent or of the whole project. And we see the coverage in color. Green means we have a good coverage. Red means we have a bad coverage. And all colors in between mean that we have some good, some bad. On the left side, we see coverage versus code size. The bigger the block, the bigger the code. And on the right side, we see coverage versus code complexity according to McCabe, cyclomatic complexity, the number of decision points in code plus 1. So the dashboard gives an overview over the testing activities and where we should focus our testing. And usually you should focus on the red parts and the most complex parts so that you make sure to have the complicated software tested, well tested. Another thing that I wanted to show with Vectorcast is that we can do unit testing. And we can create a unit test environment from scratch. This is pretty simple. Just select so first thing is we need a name. So let's test, forgot the name of the file, but let's choose a random name. Just a second, create unit test environment interactive. UT, I think it's Madlib. And then we have to select the file that we want to test, and we say build, and this will automatically build a framework around the code to build a unit test executable. It will compile and link, and we will have the option to create test cases. Now, when we create test cases, we should do the first thing we should do is a functional testing. For that purpose, I imported requirements from my requirements management system into my test environment. And now when I want to create test cases, for example, on this one function, I can right-click the function and say insert test case. And at the bottom, we see on the left side the list of requirements that are imported into the tool. And on the right side, we see the requirements that are linked to the specified test case that is open. So first things first, we want to create a test case, and we see the function that we want to test. We see the interface parameters, and we see the return value. We also have access to subprogram to the interfaces. We could specify values to be checked or values to be returned, but in this case, no stubs will be called, so it's no use in looking at the stubs. We want to do functional testing, so we are looking for the requirement that specifies the functionality of this one function that we want to test. In this case, it is this requirement, VECT629. And when we look at the requirements, it says, or at this requirement, it says that it should add up to 8-bit numbers and return the sum. And in case of an overflow, it should return 255, which is the maximum value. So let's say we create 1, 2, 3 test cases. For example, we want to check that 1 plus 1 equals to 2 and execute the test case. So this works. Let me see, we're happy. We can duplicate test cases and, for example, check if we can add 0 and 255, and this should result in 255, which works. And then let's check the final requirement, which was that when we have an overflow, then the function should return 255, which is the maximum value. So let's add 255 to the value of 1, and we would expect 255. Now, surprise, surprise, instead of 255, we get 0. And why is that? When we look at the source code, we see that this is the implementation of the function. And we see that we do an overflow check, and the overflow check adds x plus y and checks whether we have an overflow, so whether we go over the maximum and then start from 0 again. But obviously, this code is not executed even though we added 255 to 1. So we would have expected to run this code. Now, the reason why we don't cover this line, even though we have an overflow condition, Kev will explain details, I hope, in a second. So just as a short explanation, the code that is generated by the compiler, in this case GCC, is using more than the 8 bits. So the X and Y are tied to 8-bit. They cannot go beyond, but when GCC computes the result, it uses the full integer range of 32-bit, so there is no overflow. That means in this case, the correct or a better implementation would be, and we can even do that. Let's just quickly change this thing. I'm already over my 10 minutes that I would try to use to spend. So when we check that we don't go beyond 255, for example, then we will return the maximum value. So we can save and we can then rebuild the environment and then rerun our test cases. And in this, now this time they should pass, we hope. And we should see 100% code coverage on that one function by executing the 3 test cases. So here we are, we rebuild the unit test environment, we re-execute the test cases, we have 3 passing test cases, and we have a 100% covered function. Now finally we can go back into our project view. We can incrementally rebuild the environment because this change to the source code also has an effect on some of the system level test cases. So VectorCast checks which system level test case is affected by the source code change. It re-instruments the code, rebuilds the application, reruns affected test cases, and feeds the additional coverage into the system test project, or it updates the coverage for the existing test cases. So in our case, it executed or re-executed 2 test cases that ran the code that we just changed. So I'm sorry that it took longer than I intended to take, and now I pass over to Kev, and he will show us something on his side from from his tool, from Semmle. Thank you.
So my name is Kevin Backhouse. I'm a security researcher at Semmle. I focus mainly on C and C++ applications. And so I'm going to talk a bit about how to secure the software that runs the Internet of Things. And specifically, I'm going to be talking about something that we call variant analysis. This is about how you can better respond to either safety or security vulnerabilities that are found in your source code. Okay, let's go to the overview slide. All right, so the agenda is, first of all, I'm just going to go over the bug that we're using as an example today. I'm just going to kind of explain that bug in a bit more detail so that we've got something concrete so that the rest of the discussion makes a bit more sense. After we talked about that bug, I'm going to step back and talk about the big picture a bit. So I'm going to talk about the incident response process and sort of what you need to do when a bug is found in your software. And I'm going to talk about how you can try to prevent similar bugs from happening in the future, and also how you can be ready to respond quickly to new threats when they come in. Then in the third section, I will go to, I'll do a demonstration. I will show how we can use Semmle's QL query language to detect bugs like this. And I'll also show how our LGTM cloud server software can kind of automatically monitor your software projects. Okay, So let's go to the slide about the bug. So this code is a common technique that you find in C and C++ code. It's used to detect integer overflows. So if you're about to add the variables v and b together, and you want to detect whether that addition might overflow, then you can write an if statement like this. So this is specifically related to unsigned integers. If the addition overflows, then what will happen is it will wrap around, and you'll end up with a result that's smaller than either v or b. So this is a way to detect that there wasn't any overflow. The problem is if the types of v and b are small types, like, for example, they're an unsigned char or an unsigned short, and if your int type on the machine that you're running it on is bigger than that, then the way that the C and C++ programming languages work is that they do something called promotion, which means that it will actually compute the plus in an int type and not in the smaller type. And so if, for example, v and b are unsigned chars, so they're 8-bit numbers, then the calculation here will actually be done in 32 bits, and it won't overflow. And so this overflow check will actually fail. This probably seems like quite an innocuous little bug, like it wouldn't really matter, but in fact, integer overflows can have very serious consequences. So if you're working on a safety critical system, like, I don't know, a car braking system or car steering, or if you're doing something that's security critical, then this can actually have very serious consequences. So in the case of the car braking system, maybe this number that you're computing is part of an important calculation, and having the integer overflow could give you a completely wrong answer that could cause something very unexpected to happen. Or in the case of security critical software, sometimes, and we've seen real world examples of this, an integer overflow like this could maybe enable an attacker to then trigger something like a buffer overflow as a result of the integer overflow, and through a series of steps then actually be able to trigger an exploit, maybe even get remote code execution in your application. So this looks like an innocuous bug, but it can actually be very serious. Let's step back and talk about the big picture. So suppose a bug like this is found, then what do you do? Obviously, the first thing is you need to determine what the bug was, and you need to fix it. But what you also need to do is you need to make sure that you don't have any other bugs that are similar to it. So, I mean, in the case of the case where it's a safety problem, you obviously don't want any accidents to happen as a result of a bug in your code. And so it's very important that you make sure that you found all the problems. In the case of a security vulnerability, you need to make sure that there aren't other security holes that are similar to it in your application. And so part of the reason that we talk about variance analysis is that bugs are not usually unique. There's quite a good chance that if you've got one bug like this in your code, that you might have others. And there's a variety of reasons for that. One is that it might be that the same developer has worked on different parts of the code and maybe made similar mistakes elsewhere. Or it could be caused by cut and paste, where somebody else, a new programmer, came onto the team and wasn't totally sure how to do something, and so looked at how it was done in one place and then copied the same technique in a different place. Or it could be that the bug is due to a kind of a confusing API. It might be that there's a kind of a a gotcha in one of your internal APIs, and as a result of that, there's a good chance that other people will have made the same mistake. So this is what we're going to talk about today, is how you can improve this incident response process so that you can discover all the variants and also prevent future bugs from being prevent similar bugs from being introduced in the future. Okay. So what I'm going to talk about now briefly is what Semmle is and what our technology does that can help with this problem. So our big idea is summed up as code as data, so the first box on this slide. What we do is we take your source code and we turn it into a database. So that makes your source code queryable. What we then have is we have a query language called QL, which is a very powerful database query language that is also very, very well suited to writing queries that find coding patterns. So it's very well suited for that purpose. And then we have two products called QL and LGTM. So QL allows you to write queries over your source code. What LGTM allows you to do is run those queries over your whole software portfolio. So most organizations have more than one code base. And what LGTM allows you to do is take a query and run it over all of your projects and also continuously monitor all of those projects. And that allows you to get insight into what's going on with your software. All right, so now this is essentially the same slide that we saw before, but with a bit more detail added to it. So it's got the same four main boxes where you've got a bug, you diagnose, you discover variants, and you prevent future bugs. But what this is about is how you can use QL to enhance this process. So this slide was actually written mainly with security in mind, but the exact same principles apply to safety problems as well. So the first box is a bug is discovered, and that could be because you had a security team looking at it, or it could be that a customer reported that there was a problem with the device that they were using. So there's a variety of reasons, variety of ways that the bug could have been discovered. And so then obviously you need to diagnose what the problem is and fix it. But so then the thing that you can do with QL to enhance the rest of the process. So with QL, you can codify what the bug is. You can write a QL query that identifies that sort of bad coding pattern. And usually this is an iterative process where you write a query, you look at the results, you discover that there's a load of false positives that you're not interested in, so then you refine the query a bit more, and you end up with a query that is very accurately able to identify just the bad coding pattern and very few other false positives. And so that then allows you to find other variants of the bug and fix them all. So now you've improved your software much more than if you just fixed the one bug that caused the problem that was originally found. Now, the other benefit of doing that iterative process of refining the query is that now you have a query that doesn't have many false positives, and so you can use it to continuously monitor your software in the future. And so that's where you can use LGTM to automatically monitor your projects and run this new query on it to make sure that no new bugs of this kind are introduced. All right, so what I'm going to do now is I'm going to switch to the demonstration, and I'm going to show these two products that I've been talking about, QL and LGTM. So I'll start with QL and show how we can write a query that finds the bug that we've been talking about. and then I'll switch over and show LGTM and its monitoring capabilities. And I'm now going to switch to Eclipse. So the QL query language is something that you can use on lgtm.com, but you can also use it in Eclipse. So we have a plugin that you can download and install in Eclipse, and then you can write QL queries in there. So I'll actually also just briefly show you LGTM. So this is the project that we're going to be looking at. This is a project that one of my colleagues created, and it's got this instance of the problem that he inserted into the project. So that's what I've done is, using this button here, I've downloaded the database that I can query it inside Eclipse. So I'll switch back to Eclipse now. We'll look at LGTM again later. So this is the database which I've imported into Eclipse, and you can click on it and say, use this database. And so now we're able to run queries on it. I can do that here by opening up the query window. So the pattern that we're interested in looking at is this. It's x plus y less than x. That's the simple code pattern that we're looking for. So what we're going to do is we're going to say we're interested in looking for an add expr, A, and a relational operation. So relational operation is kind of less than, greater than, less than, or equal to. It covers all of those categories. And the add expression is one of the operands of the comparison. So we're going to start with that, and then we're going to refine it and make it better. Let's just see what results that gives us. Let's pull the query back up again. So I'll start. Oh, there we go. There's the results. We can see there's an example of something that it finds. So here we've got the addition that we were looking for, but what we don't have is we don't have the same expression appearing on both sides of the comparison. So that's a key part of the pattern that we're looking for, is that there's an x on the left and on the right. So let's now refine the query. Oh, by the way, you can see here that we found 36 results, and so most of them are going to be false positives. So that's why we want to refine the query now. So we're going to refine the query by saying, well, there needs to be a variable that appears on both sides of the comparison. So one of the operands of the addition is an occurrence of x. And also, one of the operands of the comparison is an occurrence of x. Let's see what we get now. Okay, so we got two results. That's the one that we're actually looking for. And this is another one that is in fact a false positive. The reason it's a false positive is you can see that the type of L is size T. So that's going to be, depending on your platform, probably either a 32-bit unsigned number or a 64-bit unsigned number. And so neither of those are going to be vulnerable to this problem. So what we can do with QL is we can also look at types of expressions and filter based on those. But what I'm going to do first is just going to show you how you can actually get more information in your results list, which can often be useful when you're trying to diagnose what you're looking at. So I'm going to print out the type of both operands of the add expression. I'm going to use something here called getOnSpecified type. I mean, in C, you often have type defs. I don't really want to see the type def. I want to see the real type that it actually expands to. So that's what getOnSpecified type does. And then we'll do the same thing with the right-hand operation. Okay, let's run that. So you can see now that the first result, it says that the types are unsigned char, and the second result, unsigned long. The other thing we can do with the type is we can actually find out how many bytes it is. And that's what we're going to use to filter in a minute. Obviously on this project, my query is only producing 2 results, which is, so the false positive rate is not very bad at all. But if you want to make this query good enough to be able to run across your whole portfolio, you really do want to be excluding this result because it's not interesting. So we can see here that it's told us that the first one has the operands are 1 byte, and the second one, the operands are 8 bytes, because I compiled this code on a 64-bit machine. Okay, so let's filter out the second result. We can do that like this. So we're going to use for all to apply this restriction to both arguments of the add expression. So I'm just going to cut and paste this business here. So we want the size to be less than 4 for both arguments. And so you see now we've just got the 1 result. So this query is now producing much more accurate results. Okay, so that's the end of the QL demo. What I'll do now is I'll switch to LGTM and show you how you can use LGTM to automatically monitor for this kind of thing. So this is the project that we uploaded with this example. And you can see here it's got 3 alerts. And the first alert is this, this problem that we're looking for. If you want to know a bit more about why you're getting this problem, then what you can do here is you can see it in context. So this now takes me to the results, and I can see it in context of the whole source file. The other thing that you can do is you can click on the query help, and this explains more about the query. And so it gives you some examples of the kind of code that would cause you to get this alert, and then how you might fix it. Now, the other interesting thing you can do is, and this is going to show you how you can track this across your whole portfolio. On this query page, you can also look at all of the alerts for this particular query. So you can see down here, this is the one that we introduced. So this one is a fake result. We created this project with this result in it. But the other ones are real. And so this one here is kind of interesting. I checked all these results, and I don't believe any of them are genuine vulnerabilities. I think they're just bugs. This one's kind of interesting. So if we click on here to see it in context, this code is calculating a checksum, and it looks like, I think what's going on here is they're trying to do a 1's complement checksum rather than a 2's complement checksum. And so when this calculation overflows, they're adding an extra 1 to the checksum value. But of course, this check is not going to work. And so I think what this means is that they're occasionally going to produce the wrong checksum. So probably fairly harmless bug, but almost certainly a bug. And actually, it's kind of interesting. I was interested to know what this project is. Let me just see. where do I get? Oh yes, here we go. There's the GitHub link. So if we go to the GitHub link, it turns out that this PX4 thing is in fact a hobby. It's autopilot software for one of these kinds of drones. So this is in fact an IoT thing that we're finding here. Okay. Now there's one final thing that I want to show you. As well as sort of showing the project, the progress of your project over time. I mean, it's not a particularly interesting picture for this project because it's one that we created. But what we can also do is we can automatically check pull requests. So LGTM integrates with GitHub, and we can go here to the link for the GitHub project here. And what I've done is I've created a pull request against this project where I've deliberately inserted another instance of this bug. And if you go and look at the pull request, then you can see that what's happened here is that I created the pull request, and then LGTM posted a comment on it which says, you've introduced a new alert. And you can see, if I just hover over here, so I submitted the pull request at 1:06, and then 4 minutes later is when LGTM posted this comment. And so this is a very effective way to prevent bugs from getting introduced into your code base, because this is the easiest time for developers to fix the problem. When they're actively working on the code, looking for feedback on the code that they've just written. If you can automatically detect problems at that point, then that is by far the most efficient way for developers to respond to that and fix the bug so that it never even makes it into your master branch of your project. Okay, that's the end of the demo. So I'm going to switch back now to the presentation. I just got a couple more slides to show. So now this is the agenda slide that I showed earlier. I've talked about most of these points already. The one thing that I didn't really talk about yet was item 2C, responding quickly to new threats. So something that we've done relatively recently is we've actually open sourced all of our QL queries. So all of the queries that we run in LGTM, all the standard queries are on github.com, on Semmle's GitHub page, so you can see exactly how they're implemented. And what this means is that you can now get community-powered security. So we have a number of customers who have some of the greatest security teams in the world who are using QL. And so if a new type of vulnerability is discovered, kind of a good example of this might be something like the zip slip vulnerability, which was discovered by Sneak's security team a little while ago. That was a vulnerability that was kind of a misuse of an API. So if you're using a library to do unzipping within your application, then it's very easy to have a path traversal vulnerability in your code. And what they found was that there was lots and lots of software projects that had this exact same vulnerability because they're all writing their own code to unzip files inside their application, and they hadn't considered the possibility that there might be a path traversal in there. And so this is where the fact that QL is open source can make a huge difference, because you don't have to wait for us or some other static analysis vendor to implement a check for this problem. Anybody can upload a solution. Anybody can write a QL query upload it on GitHub, create a pull request, and you can then immediately go try that out. And so this knowledge can be shared amongst security teams, and so the response time can get much faster as a result of this sharing of QL. Okay, and that's the end of my presentation, so I will hand back over now. Thank you very much.
Thank you, Kevin, for your presentation. It is now time for the Q&A session. Please feel free to send us the questions you probably have using the question window. Ingo, do you got any questions you can answer so far?
Yeah, thank you. Indeed, there are some questions. So first question, or there are some questions on requirements management tools, for example, whether we support DOS or Codebeamer. So the requirements gateway that we use, or the way we import requirements into the test tool is we have a Python script, and the Python script allows you to import requirements from more or less any requirements management tool. We prepared some solutions for different requirements management tools, like, for example, DOS, Codebeamer, Rectify, PDC Integrity, Team Center, I don't know, Word, Excel, Polarion. So there are a few on the list where we already have Python scripts available. And in case you have your own grown tool, or you use something that's not on the list, then you can adapt the Python script to import and export requirements and test cases linked to requirements. Here's a question on Canoe, whether we can use VectorCast with Canoe. So, well, yes, we can measure code coverage with Canoe test case. You just need to instrument the code to measure code coverage. We can, for example, transfer the coverage information from the embedded device via the CAN bus to get the coverage from Canoe test cases. And yeah, in system level testing with this Python script, I mentioned that we can ask Canoe for test cases and then execute the test cases from VectorCast. So one prerequisite, it requires that the test cases were created with Vita Studio and then created in Canoe, and then we can ask Canoe which test cases do you have implemented, and then run them from VectorCast. There is another question on code coverage, whether we can measure code coverage from the binary without instrumentation. No, that's not possible. We do measure code coverage using source code instrumentation, and that means that the binary trace cannot be used. We have to instrument. Another question on requirements, where did they come from? So I guess this question is related to the unit test tool, where I showed that we can link requirements to test cases. Yeah, we can import them using a Python script and then link them to the test cases. Here's another question on stubs. Where did stubs come from? Whether we ran gmod or something. Well, no, stubs are created by VectorCast. So the way we build a unit test environment is, well, the first thing is we call the preprocessor part of the compiler, and the preprocessor expands header files and expands macros, and then we pass this result of the preprocessing process. So VectorCast knows all the types, knows all the function calls, all the functions that are called by the unit under test. And then we build stubs for those functions, for those dependent functions that are implemented outside. Those stubs are created automatically by Vectorcast in the process of creating this unit test environment. I think that's it from my side. Yeah, so I see some questions for Kev. Winnie, well, back to you.
Thank you, Ingo. Kevin, same question to you. Do you got any questions you can answer?
Okay, so we got a few questions. I'll read them out and then try and answer them as best I can. The first question is, the example that you showed demonstrates localized analysis. Is it also possible to track vulnerabilities that are across a complex control or data flow spanning many function calls? So the answer to that is yes. The example that I showed you was really quite a basic example of QL. We can do much more sophisticated things. And in fact, in QL, one of the great things about it is that you can import libraries. So you can write very sophisticated queries with still a relatively small amount of code just by saying something like import semmle.code.cpp.dataflow. And then now you've got access to our dataflow library, which allows you to do this kind of thing. But still in only sort of less than a page of QL. But you can do this kind of thing where you're tracking vulnerabilities across, taint tracking essentially, where you've got some tainted data that comes from somewhere and then it flows to somewhere where it's used in an unsafe way. You can do that kind of thing very, very easily with QL. Okay, the second question. Is it possible to define a general rule to check any parameter which is from a public API call is checked or sanitized prior to being used inside the program? Okay, yes. So the dataflow library that I was just talking about is very configurable. So what you can do is you can override a method. QL actually, I didn't really show this, but QL is an object-oriented programming language, and so you can define classes, and you can inherit from methods and override them in the same way that you would in another object-oriented language. And so the dataflow analysis is a class, and what you can do is you can override the isSanitizer method. And so then what you can do is you can say, well, this particular type of code is doing sanitization of the input, and so if the data flow reaches this point, then it should stop and not continue, because beyond this point, the data is actually safe, it's been sanitized, and so I don't need to worry about it. So yeah, so that's something that you can certainly do with our data flow library. And those data flow libraries, by the way, are available for multiple programming languages. So we support C, C++, Java, JavaScript, Python, C#. Those are our main languages, and all of those have data flow libraries that you can use to do this kind of thing. Okay, question 3. Can the custom rules be used in a continuous integration process with a tool like Jenkins? Yes. I mean, well, first of all, LGTM is itself really a continuous integration process. It's continuously monitoring your software projects and giving you feedback on them and doing things like commenting on your pull requests. But it also has an API which you can use to integrate with Jenkins in particular, is one that you can use to integrate with. And the kind of things that you can then do with it is you can actually make it impossible for somebody to merge a pull request until the issues have been fixed. That's something that you could do using this API. So you can make it even stricter, that it's not just commenting, it's actually blocking your pull requests until you fix the issues. Yeah. Okay, so that's all for now. But if you have any other questions, then please do email me, and I will respond over email. Thanks.
Thank you, Kevin. I see that there are still some questions to answer for Ingo and you, but our time is gone now. I think we will answer all questions after the webinar by email. I would like to come to the end of this webinar about securing the software that runs the Internet of Things. I'd like to thank Kevin and Ingo for their presentations. Thanks to all attendees for your interest and the time you spent with us today. I hope you enjoyed the webinar and we can welcome you again at one of our next webinars. I wish you all a great day and a successful week. Goodbye.